What is project problem-based learning, and why are teachers and students so excited by it? Perhaps the best way to begin is to describe how it differs from traditional learning. In traditional learning, teachers lecture and students listen. To be honest, even the most interesting teacher can bore students because they're not actively participating. They're just sitting there taking in the content. Often, it's more about memorizing information to answer test questions than learning. There's an old saying, it's not what the kid does to the wood that matters, it's what the wood does to the kid. The meaning of this simple saying is deep. Wood is just a material, but how a person uses it to design, build, evaluate, and engineer a product, that's what creates the kind of learning that is most important. It's not just about mastering a skill or a procedure. For example, when CAD software was introduced and the CNC machine came out, lots of teachers jumped to develop courses focused on teaching the procedural skills to master the software for the machine. Students went to a CAD class, copied an image, and made a 3D model. The emphasis was on mastering the software commands to create that pretty picture. There was no original design, no original thinking. Picture a traditional lab where students go to perform a required list of projects. Often they just make a clone of an item. Once again, there is no original design, no critical thinking, and no teamwork. This is very different from project problem-based learning, which is focused on rigorous and relevant problems that students can relate to. And the projects are designed to be about real-world items that are rigorous enough so that we can build a relevant project-based, problem-based curriculum. Here's another big difference. The teacher isn't a sage on the stage. The students lead the learning, and the goal is for them to solve the problem. The teacher facilitates and helps the students reach the point where they have a possible solution to a design problem. The students research and work to come up with an original design. Throughout the process, they document that work using their engineering notebooks, doing the design briefs, working in teams, and making presentations. At the end of the project, they defend their design solutions in front of an authentic audience. The classwork is usually done in teams of 2 or 3 students, called cooperative learning groups. But it's important to make sure that each student on a team is responsible for all the learning. It's critical that this curriculum provides room for more than one right answer. You don't want every student to come up with the same solution. That means you need to be good at writing what is called the essential question. It's an open-ended question that can only be answered by describing the problem solution, and there is more than one possible solution. In PPBL, the teacher guides the students through the questioning. The questions are intended to keep the students within the parameters of the critical path so they can identify the problem's solution and communicate it. There is formative evaluation using rubrics, and summative evaluation is available through the Siemens certification exam. So here are some examples of essential questions. How can we design, build, and evaluate an automated thermal solar collector that heats water, and explain the system's performance using mathematics? The question is open-ended, challenging, and relevant. Here's a second one. Can we design, conduct, and quantify the results from an experiment using a human subject to measure the effect diet has on the performance of an endurance athlete? Let's say you use a marathon runner for this. You would need to know what they ate before their marathon because it certainly affected their performance. But how would you quantify that? And when you have an experiment using a human subject, there are very specific government-controlled procedures that must be followed. Here's a third example. Can you use a science concept to design, build, and evaluate an automated device that can measure the distance a person is from that device? How would you do that? You might create something to send out a pulse of energy that hits the person and then comes back to what you've designed. By measuring the intensity of what bounces back, you can develop an algorithm to determine the distance. This is radar. So that's one concept in science. Another one might be to use light intensity. Before smartphones, cameras had strobe lights. You would take a picture and the strobe would send a blast of light to the subject and then return to the strobe. When the amount of light was perfect for the picture, the strobe was shut off, leaving the perfectly lit amount of light on the subject. So that might be another solution. The key words that are in essential questions are design, build, evaluate, and quantify. Next, let's look at the depth of knowledge chart. Look at level 1. It's about recall. Level 2 is about skills and concepts. When you look at the words in those two levels, you see things like recognize, memorize, organize, construct, modify, and predict. These are words that describe the kind of learning that exists in a more traditional curriculum. With the Siemens engineering design curriculum, students are working a bit at level 3 and mostly at level 4, where there is strategic and extended thinking. Look at the difference at what occurs at these levels. Students design, connect, synthesize, apply concepts, critique and analyze, create, and prove. When you look at the curriculum and the learning standards that have been developed for projects, you will consistently find the depth of knowledge at levels 3 and 4. It's this kind of thinking that brought us amazing inventions over 3 revolutions. The 4th revolution is now underway. Eric Drexler from MIT calls it the atomically precise manufacturing revolution. Think about what a 3D printer can do. It can receive a model from a CAD system and lay down plastic material in layers to produce a 3D model of the design that was created in a CAD system. There are now 3D printers that can produce precise quality models that can go right into cars or other products. Sometimes the parts are plastic, sometimes powdered metal. No matter what the material, there are different ways of producing parts that can eliminate traditional manufacturing processes. In 2013, Eric Drexler published Radical Abundance: How a Revolution in Nanotechnology Will Change Civilization, and wrote about how this revolution, like others, will transform how we work and live. So what does this mean for education? It means we must change teaching and learning to be more relevant. Project problem-based learning is the key.